Hello, this is Professor Kitch, and welcome to this webcast on Section 12.9. This is the first of two webcasts covering laboratory shear strength tests. This presentation is on the direct shear test. When you finish this presentation, you should be able to describe the direct shear test and draw a schematic of the test equipment. In addition, given data from a direct shear test, you should be able to properly plot the data and determine the strength parameters for the soil which was tested. This figure shows a plan view of a typical direct shear test box. The soil sample used in this test is cylindrical in shape with a cross-sectional area of A sub s, and it's contained in a donut-shaped rigid metal shear box. To understand the operation of this test, it's best to look at a vertical cross-section through the shear box. For the rest of this webcast, we will be looking at a vertical section cut through the shear box at BB' shown here. This figure shows the vertical cross-section BB'. The shear box is split in half at its mid-height by a horizontal plane. This separates the shear box into two pieces called the upper and the lower shear box. The soil specimen is contained in the shear box and sandwiched between two porous stones, one above and one below the specimen, as shown. The purposes of the stones are to distribute the loads evenly to the soil and to allow water to pass freely in or out of the specimen. This prevents the buildup of excess pore pressure during testing. The lower shear box is attached to a rigid base and placed in a water bath. A vertical force F sub z can be applied to the top of the upper stone. This force will generate a normal stress sigma in the specimen, which will be equal to F sub z divided by the cross-sectional area of the specimen, A sub s. Since the box is split, the upper box can move separately from the lower box. By applying a horizontal force F sub x to the upper shear box, we can generate a shear stress tau in the specimen. The magnitude of tau will be equal to F sub x divided by A sub s. Because the box is split in the middle, a shear plane will form along the dashed line shown in the figure. A normal stress sigma and a shear stress tau will be generated along this shear plane as shown. During the test, we used dial gauges to measure the horizontal displacement of the shear box, delta sub x, and the vertical displacement of the top of the specimen, delta sub z. Now let's see how the specimen is sheared. After the vertical load F sub z is applied, the horizontal load F sub x is gradually increased. This generates a shear displacement in the specimen. The dial gauges record the horizontal and vertical movements during shearing. The vertical force and therefore the vertical stress in the specimen are constant during testing, while the horizontal force and the shear stress are increasing. As we just noted, during the test, the vertical or normal stress will remain constant. In this case, we will assume the normal stress for the test is equal to sigma 1. As we increase the applied shear stress tau, we will record its magnitude as a function of the horizontal displacement delta x. Depending on the nature of the soil being tested, the plot of tau versus delta x will have one of two shapes. In one case, the applied shear stress increases to a peak level, then decreases with additional displacement, finally reaching a plateau. In this case, the greatest shear stress measured represents the peak strength and the value of shear stress at the lower plateau represents the residual strength. This shape of shear displacement curve is typical of dense sands or over-consolidated clays. The interlocking of soil particles in these soils generates relatively high shear strength. As this strength is exceeded, the particles start to slide and roll over one another. This causes an expansion or dilation of the soil in the shear zone, and the strength of the soil is reduced. The strength loss eventually levels off as the soil reaches a new equilibrium state. The second shape of curve shows a monotonically increasing shear stress as the horizontal displacement increases. It eventually reaches an asymptotic peak strength. This case is typical of the behavior of loose sands or normally consolidated clays. In these soils, the shearing process causes soil particles to rearrange themselves into a denser configuration. This causes contraction or densification of the soils in the shear zone, and the soil gains strength until it reaches its peak value. This particular figure illustrates one soil, say a certain sand. tested in both a dense and a loose state at the same normal stress. In this case, the peak strength of the loose sand will be equal to the residual strength of the dense sand. In both cases, the soil will reach the same equilibrium state at large displacements, because both tests were performed on the same material at the same normal stress. Remember that the normal stress during a direct shear test remains constant. As we just described, the soil will usually change volume during the shearing process. We can measure this volume change in a direct shear test by observing the vertical displacement during testing. Because the cross-sectional area of the specimen does not change, any change in volume will generate a vertical displacement in the specimen. If the soil is dense, it will dilate or increase in volume during shear, and the displacement at the top of the specimen will be upward, as we see here. During the shear test, we record the vertical displacement at the top of the specimen as a function of the horizontal displacement. Here, we see a typical plot of the vertical displacement versus horizontal displacement for a dense sand or an overconsolidated clay. There is a small amount of downward movement of the specimen at the start of shearing, but it's followed by a larger upward movement indicating that the specimen is dilating during shear. The opposite of dilation during shear is contraction, or a decrease in volume. This occurs when the soil is loose and gets denser during the shearing process. In this case, the displacement at the top of the specimen will be downward, as we see here. Here we compare the previous plot of vertical displacement versus horizontal displacement for a dense soil with that of a loose soil. The loose soil is contracting during shear or becoming denser, therefore the vertical displacement is downward, as we see here. Thus far, we've looked at the results of a single direct shear test and explained the difference between contractive and dilative behavior during shear. Now we want to use the results of a direct shear test to determine the strength parameters, the friction angle phi and the cohesion C, for a given soil. In order to accomplish this, we must run a series of direct shear tests on the same soil at different normal stress levels. This figure will present the results of a series of 3 direct shear tests performed on identical specimens of the same soil. Here we see in black shear stress as a function of horizontal displacement for one test run at a high normal stress, sigma 1. A second test, shown in blue, was run at an intermediate normal stress, sigma 2. And a third test, shown in green, was run at a low normal stress, sigma 3. For each of the 3 tests, we can determine the peak and residual strengths, as seen here. To determine the friction angle and cohesion of the soil, we must develop a more Coulomb plot of the shear stress versus effective stress. In the direct shear test, we measure the shear and normal stresses on only one plane, the failure plane. Therefore, we cannot generate a Mohr circle for each test. Instead, we simply plot a single point representing the shear and normal stresses at failure. The triangles shown here represent the peak shear strength measured from the previous figure. If we fit a line to these points, we can determine the effective peak friction angle, phi prime peak, and the effective cohesion, C prime peak. Similarly, we can plot the residual strength values as shown here by the squares. We then fit a line to these points and determine the effective residual friction angle phi prime r and the effective cohesion C prime r. This particular plot illustrates data that might be measured from testing an overconsolidated clay soil. This can be determined by the significant cohesion measured from peak strength. The residual cohesion is generally very small or near zero, as we see here. If we had been testing a dense sand, the plots of strength versus normal stress would have generated 2 strength envelopes, such as those shown in this figure. Neither envelope would show any cohesion, but we would have different peak and residual strengths. If we had been testing the same sand in a loose state, we would have measured just one set of strengths, and the single peak strength envelope would appear as shown. This would be identical to the residual strength envelope obtained from the same sand in a dense state. There are a number of limitations to the direct shear test. These include the following. There is no control over drainage in the specimen, and we cannot measure pore pressures during the test. Therefore, the only way we can know what's really going on is to run the test very slowly so that any excess pore pressures that might be generated can dissipate. In this case, there will be no excess pore pressures and the effective stress will be equal to the total stress. In this test, we force the soil to fail on a predetermined failure plane, which is always horizontal. This may or may not be the weakest plane in the soil. The actual stress state in the failure zone is much more complicated than the simple model we assume in our test. Finally, because the actual conditions in the shear zone are complex, we cannot determine the strains during the test. Therefore, while we can determine the soil strength, we cannot determine the stress-strain properties of the soil with this test. In summary, the direct shear test has the following characteristics. The test is easy to set up and run. For clay soils, the test must be run very slowly, sometimes taking over a day to reach failure. The data is relatively easy to analyze. We can measure the volume change during shear to determine if the soil is dilating or contracting. The shear strength parameters measured in this test are less accurate than those measured in triaxial tests. This is mostly due to the fact that we constrain the soil to fail on a certain plane rather than letting the soil fail on whatever plane it would like to. This now concludes this presentation. You should now review your learning objectives. It would also be a really good time to review example 12.9 in your text. Try and complete this example before class.
Eso es todo, amigos.